A transfer function describes how a system modifies the amplitude and the phase of each frequency component of a signal. So first, if the input signal is expressed as a series of sine or cosine. Now first look at one by one. The first term is a DC term, so the frequency is 0. The second term here is a cosine. We should compare this term with cosine omega t plus the phase angle. Now the omega t can also represent, we write this one as cosine 2 pi frequency t plus phase angle. So it's very clear now, the frequency of the second term is 500 Hz. And the same argument here, because this is already a pi, all you need to do is divide the 3000 by 2. So the third term is frequency is 1500, and the fourth term, the frequency is 3000. V in this time, at each frequency, we're going to write down the amplitude and the phase of each term. So for example here, for the first term here, there's only amplitude because there's no phase, so this is 2. The second term, the amplitude is 2 and the phase is 30 degrees. So we can write this one. It means under 500 Hz, under this frequency, the amplitude is 2 and the phase is 30 degrees. Next, the third term is 2 minus 20. So 2 and its phase is minus 20 degrees. The last term, the amplitude is 2 and the phase is 0. Next, we look at each frequency here and see how the transfer function will alter or modify the amplitude and the phase. So 0, so we look at the 0. At 0 frequency, remember this is frequency, and the transfer function for the amplitude 4. So we can write this one as 4. If this is 1, it multiplies 4. How about the phase? The phase here is 0. So this is 0 degree. It doesn't change the phase. Second, 500. So we look at 500 here. And we can say from here, at 500, if you look at this graph here, it's very clear it is 3.5. So this becomes 3.5. It means it will multiply any amplitude by 3.5. How about the angle? If this is 500 here, and this is very clear is 15 degrees, and this is positive 15 degrees. Next, we want to look at 1500. So 1500 here, and this is 2.5, and 1500, and this is 45 degrees. And now we have 3000. 3000 here is 0. Now it means you can see from this line here, after 2500 Hz, the frequency or the transfer function becomes 0. It means it after 5000, after 2500, it cuts off. There's no more transfer. So this is 0. And the amplitude, of course, the phase is also doesn't matter because the amplitude is already 0. Now next, we have to find the output and write it down in with a phasor. So next is 4. If this is 1, it becomes 4, but you have 2 here, so this is become 8. and the angle, of course, 0. 3.5 multiplied by 2, so this is 7. Now, this one means you shift the phase angle by 15 degrees, so it means it becomes 45 degrees. Here, this is 5 minus 20 plus 45, so it becomes 25 degrees, and this is 0. So now you can rewrite this one as the first term become 8, and the second term, which is 500 Hertz, the amplitude is 7 cosine. Now you have to write here this term. This is 500 Hertz and multiply by 2. So I just keep 1000 pi t plus this time the phase changed from 30 to 45 plus the same 5 cosine. This is 3000 pi t plus 25 degrees. In this question, the input signal has 4 terms. The first term is a DC term, and the frequency, of course, equal to 0. The second term is a cosine 5000 pi t, because we have a pi when we compare 2 pi f here. So the frequency is 5000 divided by 2, so this is 2500. The third term, divide this number by 2, is 5000. The last term is 11,000. Next, we'll write down the amplitude and the phase of each component in the signal. The first is a DC term, so it only has amplitude and is 6. The second term, 4, positive 30 degrees. The third term, 2, and positive 60 degrees. The last term, the amplitude is 1, and it has a phase of 90 degrees. Next, let's look at the transfer function of each component. At DC, 0 frequency here, and it is 2, so this is 2. 2500, so this is kilo. It means 2.5 kilo. 2.5 kilohertz. And this one is 1.75. And if we look at 2.5 kilo here, and this is a negative number, and this is minus 30, minus 60, so this is in between, so this is minus 45. Next, 5,000. 5,000 here. And this is here. So this is 1.5. And 5,000. And here. Minus 90 degrees. Next, 11,000. 11,000 here is already beyond the cutoff frequency. So it's 0. So no need to worry about the phase. Now the output is we apply the transfer function on the input. So we will say output is equal to the transfer function multiply the input. When I say multiply, you have to separate the amplitude and the phase. we add or subtract the phase, the amplitude we just multiply. So 2 times 6 is 12. And 4 times 1.75, it is 7. So we multiply the amplitude, but we shift or we add the phase. So 30 minus 45 minus 15 degree. The same, 3 here, 2 times 1.5, and 60 degree minus 90 degree minus 30 degree. So now we can write down the expression in time domain. The first term becomes 12 plus 7. The second term, the time here is 5000 pi t. So cosine 5000 pi t. So the transfer function won't change the frequency, but the phase become minus 15 degree. Plus, this is 3 cosine 10,000 pi t. And the phase now is changed from positive 60 degree to minus 30 degree. That's it. Here is an RC circuit. If we get the signal from the capacitor, this is V out, this will behave as a RC low pass filter. It means the low frequency component will pass through, whereas the high frequency component will cut off or attenuate. So the transfer function can be written as this. This is the amplitude, and this is for the phase. And you can see it depends on first the frequency. It makes sense. And also RC. We have a RC circuit. For the phase, it also RC. And remember here, this is negative. So the phase angle always is reduce the original phase. So it's a negative shift. If the R here is 200 ohm and 1 mil, and we can plot this one in these two graphs. Now, with this RC value, if the input signal is described by this function, we have 1, 2, 3 terms. So let's analyze this one. First, we look at the frequency. The same argument here. For the 800 pi, we can say 2 pi f. So 2 pi ft, so the frequency is 400. The second term, the frequency is 600. The third term is 1800. Second, we write the amplitude and the phase. It means the phasor for each component or each frequency. So the first is 4 positive 30. 4 30 degree. The second term 2 positive 6, 2 positive 60. The last term 1 positive 90 degree. Next, let's look at how the transfer function will modify the signal of each term. Now we write down, we look at the amplitude first. First, this is 400, so this will be here, and it will be somewhere here, and here. So roughly, this will be okay, and you can see here, this is very close to 0.9. And the angle, if we look at 400 Hertz, so this is 400 Hertz. It may be about 26 So if you say 26, I think it's good enough, but 25 also it will be acceptable. So either you put minus 25 or minus 26, it's definitely okay, or even minus 27. So there usually a sort of ambiguity when you read this graph. And in this case, I just put minus 25 degree. Again, it doesn't really matter, 25, 26, or 27. Next, this is 600 Hertz. 600 Hertz. This is 0.8, very clear. So this is 0.8, and the angle here. And this is, I think it's very clear, is more than 35, and 37 is good enough for minus 37 degree. 18,000, so 18,000 here, and this is about 0.4, and the angle here, I would say roughly about 60, 65, and 67, minus 67 degree. Now let's apply the transfer function to the input signal. It means mathematically, we want to say output equal to transfer function applied to the input signal. And we multiply their amplitude, and we add their phases. So the first term, 4 times 0.9, which is equal to 3.6. So the phase now become 30 minus 25 degree. This is 5 degree. 2 times 0.8 is 1.6. And 60 minus 37, this is 23 degree positive. This is 1 times 0.4, this is 0.4. 90 minus 67 degree, this is positive 23 degree. So let's write down the output signal in time domain. So output, it's a function of t. The first term now become 3.6 cosine. Remember the frequency is 400. It means it become 800 pi t plus 5 degree. The second term 1.6 cosine 1200 pi t plus 23 degree, and the third term plus 0.4 cosine 3600 pi t plus 23 degree. And if you can see here, it's very clear this is a low pass filter. It's because especially the amplitude term, the transfer function, the first term for the 400 Hz is 0.9, for the 600 Hz is 0.8, 1800 is 0.4. So the higher the frequency, it will reduce or attenuate the amplitude further or larger. For a RC circuit, if we obtain the output signal across the resistor, this will become a high-pass filter. And the transfer function of the high-pass filter is described by this equation. This is for the amplitude, and this is for the phase shift. Again, if the R is 200 ohm and the capacitor is 1 microfarad, in this case, we can plot the transfer function with these two graphs. And now we have an input signal here. Let's look at term by term. First, the first term, 800, so the frequency is 400. 1600, so the frequency is 800. 3200, so this is 1600. Now we write the phasor of input signal for each component or each frequency. So the 400, this is 4, and the phase angle positive 10 degree. Second term 2, and the phase angle is positive 20 degree. The last term, the amplitude 1, the phase angle positive 30 degree. Now we have to use the graph here for the 400 Hertz, the first term here, the 400. So this is roughly about 0.45. For the angle, 400 here. About here, and this is 60 and around 63 degree. For the 800 Hertz, so this is about this is very clear, about 0.7. 800 Hertz. And this is about 45 degree. For 1600 Hertz, the amplitude transfer function is 0.9, and this one here, I would say about positive 27 degree. So now we apply the transfer function to the input signal. 4 times 0.45, this is 1.8, and it shifts the angle become 73 degree, and this is 1.4, and now it becomes 65 degree. This is 0.9, and it becomes 57 degree. So the output signal is equal to 1.8 cosine 800 pi t. The phase angle is 73 degree. The second term, 1.4 cosine, and this is 1600 pi t plus 65 degree plus 0.9 cosine, this is 3200 pi t plus 57 degree. A RC low-pass filter has R 1K ohm and C 0.1 microfarad. Now, the transfer function of the low-pass filter is written as H F 1 over square root 1 plus 2 pi F RC square. Now I want to focus on this factor 2 pi FRC. I want you to think about if this factor write in this form. So how can we write this number here? And it's very clear. This number must equal to 1 over 2 pi RC. So it means now we can define so-called the cutoff frequency or the break frequency. It depends on the discipline. So if we define the cutoff frequency FC as 1 over 2 pi RC, the transfer function can be written as a more interesting way, and this is equal to 1 over square root 1 plus F over FC to the power of 2. The phrase also can be written similar as this one, and it will be minus tangent of course, F over cutoff frequency. The cutoff frequency is equal to 1 over 2 pi RC. If you plug the number in, and you will get the cutoff frequency equal to 1.59 times 10 to the power 3 Hertz. This is F. It means you just copy this one from the given equation as long as you understand what it means. Number C, calculate the transfer function magnitude at all the three. So what I mean is, number 1, the magnitude of the transfer function. If f equal to 0.1, f over fc equal to 0.1, and the same here, f over fc equal to 1, and here f over fc equal to 10. 1, the transfer function or the amplitude of the transfer function is 1 plus 0.1 square, and the second is very simple, 1 plus 1 square, and the third one is 1 here, 1 plus 10 square. And we will plug this one into your calculator. You will find this is equal to roughly 0.995, and the second one is 1 over root 2 is roughly equal to 0.707, and the third one is roughly equal to 0.0995. Apply the filter to the input AC signal and compute the output amplitude, and then we see how the function or how the transfer function change. Now we can see how the transfer function modify the input signal, in particular the amplitude. So the output amplitude, and V out is amplitude, is the amplitude of transfer function multiply the input. And so let's look at it. If the input is 5, yep, so it doesn't change the angle, we're just focusing on the amplitude. So for this one 5, so it means if the frequency different, how the transfer function will change. So this is your system. You have a signal here, and this signal is 5 cosine 2 pi ft plus 30 degree. Depends on the frequency. Okay, and this one, how much the amplitude will change, it depends on the frequency. So let's do it. When f equal to 0.1 fc, the transfer function, the amplitude is 0.995. So you can see this frequency is only 10% of the cutoff frequency, and the transfer function is close to 1, so it's a low frequency. And the transfer function say you will get about 99.5% of the amplitude will be transferred. So the V out is 0.995 times 5, 4.98 volt. So it means you will get 4.98 volt at this frequency. If the frequency equal to the transfer or equal to the cutoff frequency, in this case the transfer function is equal to 0.707, and the output voltage is 0.707 times 5. This time you only get 3.54 volt. If the transfer function is 10 times of the cutoff frequency, the transfer function corresponding to this case is 0.0995, and the output voltage is 0.0995 times 5, and this equal to 0.498 volt. So this is very clear. For the first case, that it means this case, this is a very little attenuated and or nearly unchanged. For the second case, this is actually half strength. Okay, and for the third case is highly attenuated. Okay. For the RC high-pass filter, if R is 1 k ohm, C is 0.1 microfarad, we can first calculate the cutoff frequency. So Fc, the definition is 1 over 2 pi RC. And if you plug this one in, you will find this is exactly the same frequency as number 15. Second, write the transfer function magnitude in terms of the ratio of F over Fc. So again, you have to look up the given equation, and this is the magnitude of the transfer function can be written as 2 parts. The numerator is F over Fc. This is the frequency over the cutoff frequency. The second part, it involves a square root, and this is 1 plus F over Fc bracket to the power of 2. So this one is different from the low pass filter. Part C. When F equal to 0.1 of the cutoff frequency, your transfer function can be written as, of course, it means F over FC is 0.1. So this is 0.1, and this is 1 plus 0.1 to the power of 2. And this is roughly equal to 0.0995. Is only about 0.1, about 10%. Number 2, when F equal to cutoff frequency, the amplitude of the transfer function is again this is 1 over square root 1 plus 1. So again, you will get 1 over root 2. And this is roughly equal to 0.707. Number 3, when the frequency is 10 times of the cutoff frequency. So we have a high frequency now. So your cutoff frequency like a standard. What is mean high? What is mean low? It depends on how your frequency compare with the cutoff frequency. And this one become 10 square root 1 plus 10 to the power of 2. So this is roughly equal to 0.995. So now you apply this one to the amplitude of your input signal. So let's look at one by one. The case 1, when F equal to 0.1 of the cutoff frequency. In this case, the transfer function is 0.0995. So your output is 0.0995 times 5 equal to 0.498 volt. So you got only 10% of the input amplitude. So this is highly attenuated. Highly attenuated. Number 2, when the frequency equal to cutoff frequency, your output this time again 0.707 times 5, and this is, we call this one half power. Okay. Third, when F is 10 times of the cutoff frequency, your output is 0.995 times 5. So you got 4.98 volt. So it means nearly unchanged. So this is almost unchanged. Now I want to look at the second case here to clarify some of the interesting here. When F equal to FC and the output is equal to 0.707 of the input. So V out over V in is 0.707. Now, if you think about power is proportional to V square. Why? Because the equation P equal to V square over R. So the R is the load, is a constant. So if we look at the power of the output over the power of the input, their ratio, we will say this is square of output of the voltage over the input of the voltage. It means 0.707 to the power of 2. And if you plug this one into your calculator, you find this is roughly equal to 0.5. So it means in terms of the power, you got only half the power at this point. And if you calculate the dB, it's minus 3 dB. This is a low-pass RC filter, and our input signal has 1, 2, 3 terms. The R is 820 ohm, and the capacitor is 3.3 microfarad. A, we want to find the cutoff frequency. So FC, the definition, 1 over 2 pi RC. So if you plug this number in, and you will find this is equal to 58.8 Hertz, the cutoff frequency. Now let's analyze the term or the signal term by term. First, 400, 800, and 1600. So it means the frequency is 200, 400, and 800. The input signal for 200 Hertz is 4, and there's a no phase angle here, and this is 4, also no phase angle. 5, the phase angle also is 0. To calculate the transfer function, this time we have to find the frequency over the cutoff frequency. For example, if f equal to 200 Hertz, f over fc will equal to 200 over 58.8. So if you plug this one into your calculator, you will get 3.4 roughly. Now you plug this factor into the equation. So the equation say is equal to 1 over square root 1 over f over fc bracket 2. So you plug this one into this equation, 1 minus, this is 3.4 to the power of 2, and this is plus, I beg your pardon, otherwise you will have an imaginary number. Okay, so once you plug this one in, you will find this is equal to 0.282. Now you can also apply the equation for the phase shift. So the equation for the phase shift is in terms of the cutoff frequency. This is negative arctangent and f over fc. So you get negative arc. F over fc is 3.4. So if you plug this one into a calculator, you will find the angle is equal to minus 73.6 degree. So you repeat the procedure for 400 Hertz and 800 Hertz. So you will find the transfer function for 400 Hertz is 0.145, and the angle is minus 81.6 degree. At 800 Hertz, the transfer function is 0.0733, and the angle is negative 85.8 degree. Now we can apply the transfer function to the input signal term by term, and same argument, we multiply the amplitude and we add the phase angle. So this one will become 1.13 and minus 73.6 degree, 0.582 minus 81.6 degree, 0.293 minus 85.8 degree. So your output signal is 1.13 cosine 400 pi t minus 73.6 degree plus 0.582 cosine, this is 800 pi t minus 81.6 degree, the last term, plus 0.293 cosine 1600 pi t minus 85.5 degree. This circuit is a high-pass RC filter because the output signal is obtained across the resistor. First, we want to find the cutoff frequency. The cutoff frequency is exactly the same as low-pass filter. It means 2 pi RC, and it is equal to 60.3 Hz. The first term, the frequency is 60 Hz. Second term, it is 200 Hz. The last term, 600 Hz. The phasor for the input term by term, 4 minus 15. The second term, 4 plus 30 degree. The last term, 4 minus 60 degree. Now we need to calculate the transfer function. I just want to recall, for the high pass filter, the transfer function is equal to F over Fc over 1 plus F over Fc to the power of 2. So for the case 1, it means for the 60 Hz. So your F over Fc, let's calculate. For 60 Hz, F over Fc is equal to 60 over 60.3. So this is equal to 0.995. So the amplitude of the transfer function is 0.995 over square root 1 plus 0.995 to the power of 2. And this is 0.705. For the high pass filter, the phase angle is equal to arctangent, but be careful, this time it's reversed. It means it's cutoff frequency over the frequency. So if we plug this one in, and this is cutoff frequency is 60.3 and the frequency is 60 Hz. So if you plug this one into your calculator, you will find this is 45.1 degree. So for 60 Hz, the transfer function is 0.705 and the angle is 45.1 degree. Now you can follow the same procedure for 200 Hz and 600 Hz. For 200 Hz, the transfer function is 0.957 and the angle is 16.8 degree. For 600 Hz, the transfer function is 0.995 with an angle 5.74 degree. Now we apply the transfer function to the input signal term by term. So this is 2.82, and now this is 30.1 degree. The second term, 3.83, and now you add the two angles, which is 46.8 degree. The third term, 3.98, and the angle is minus 54.3 degree. So the output signal V out as a function of t, or sometimes we call this is the time domain. This is equal to 2.82 cosine 120 pi t plus 30.1 degree plus 3.83 cosine 400 pi t plus 46.8 degree plus 3.98 cosine 1200 pi t, and this is minus 54.3 degree.